we're going to start the day off again with some of the SSERVI awards. This time it's for the Susan Mahan Niebur Early Career Awards. And we have two great awardees. I'm going to do a little introduction and then start with one and then the second. So I'm just talking slowly because there's a few more people walking into the room. Okay, so I think many of you know about the award, but this annual Early Career Award is given to scientists who have made significant contributions to the science or exploration communities. Recipients are researchers who are no more than 10 years from their terminal degree, who have shown excellence in their field and demonstrated meaningful contributions to the science or exploration communities. So this year, our two awardees are Doctors Kerri Donaldson Hanna and Julie Stopar. Dr. Donaldson Hanna is a planetary geologist and assistant professor in the Department of Physics at the University of Central Florida. She received her BS in Space Sciences from Florida Institute of Technology and MS and PhD in Geological Sciences from Brown University. She then was a postdoctoral researcher within the Atmospheric, Oceanic, and Planetary Physics subdepartment at the University of Oxford and was awarded the Early Career Winton Capital Geophysics Award from the Royal Astronomical Society. Dr. Donaldson Hanna's research focuses on understanding the formation and evolution of airless bodies like the Moon, Mercury, and Mars's moons, or the moons of Mars, and asteroids. Dr. Donaldson Hanna is also interested in understanding the effects of particle size, porosity, albedo, and near surface conditions of airless bodies on their thermal infrared signature and how it best simulates these in the laboratory. She has participated in NASA missions, including as co-investigator on the Lunar Reconnaissance Orbiter's Diviner Lunar Radiometer experiment and as a participating scientist on OSIRIS-REx. Just last year, she was selected to lead the payload suite of experiments on the LunarVice mission, which we heard about earlier this week. So, without further ado, I'd like to welcome Dr. Donaldson Hanna. Wow. Donaldson Hanna. I'm going to put the first one and it is for you to take home with you. Congratulations. You can have the mic.
Okay, so first I'd like to thank SSERVI and my nominators. I'm certainly humbled and honored to be given this award in the name of Susan Niebur. I personally didn't ever get a chance to meet Susan, but I'm certainly in awe of her passion for planetary science and space exploration, and also really enabling early career scientists in their careers and really pushing them forward. I'm also very honored to be included in that long list of early career scientists that you saw on the early slide, many of which we've heard this week throughout the meeting, including Addie Dove and Deborah Hurwitz and Jacob Bleacher and many, many others. So in honor of Susan Niebur and her passion for thinking about early career scientists, I thought I would talk through my journey at becoming a planetary and lunar scientist, because I thought that might be very interesting to those in the room, because I didn't follow the most traditional path to becoming a lunar scientist. You know, I'm a pretty old early career scientist. And so I thought that might be beneficial to hear about. And so, but what I wanted to start with was really talking about my childhood. And I think, like many of you in the room, you know, I grew up really loving math and science and NASA and space exploration. And really that was driven by my family. And, you know, my dad absolutely loved NASA and the Kennedy Space Center. And so every year, as typical Missourians do, we would go to Florida. And one of our stops was always at the Kennedy Center or Kennedy Space Center visitor complex. But of course, in the early 80s, this is what the visitor complex looked like. And so that's a picture of me and my brother and my sister out in front of the Rocket Garden. And then also my love for math and science was really also pushed forward by my grandfather, who I have a picture of here with me. And he knew how much I loved math. And so he would build all of these sheets of math problems and send me off and say, go solve all these problems. And, you know, he would just give me endless amounts of work to do, and just, you know, it tickled him to try to challenge me and really give me a hard time, you know, challenging problems. And another thing that really I took away from, you know, working with my grandpa or spending time with my grandpa was being on the farm. And on the farm, you know, you don't get special chores just because you're a girl. You know, like, you get chores and you have things that you have to do. And he really enabled that sense of self, that I was capable of doing anything that I needed to do if I worked hard and I just persevered. And that's certainly something that I carry with me, so that when people are very doubtful or skeptical, I know that I can do it. And that really came from my grandpa. And so when I was thinking about going to undergrad, I really wanted to go someplace that I could study space, but I really had no idea what that meant. You know, even, you know, we had spent a lot of time thinking about space and visiting the Kennedy Space Center. I really didn't know what I wanted to pursue. And so I went to Florida Tech, where I could study math and physics and astronomy and planetary science, and really try to get as many opportunities as I could doing research. And so I was part of a reduced gravity flight program team where we flew in the KC-135 and flew experiments on the KC-135. I helped build a moon buggy to participate in the Great Moon Buggy Race. And I also worked for a summer as part of an REU at the University of Arizona with Ann Sprague. And I went and learned all about doing telescopic observations at thermal infrared wavelengths of Mercury. And, you know, walking away from that experience, I was like, wow, this is really cool, spectroscopy. But I mean, is that something that I could actually do forever? I mean, is that a thing that you can do? And I just really wasn't sure. And so kind of overwhelmed and in awe of like so many avenues that I could take. When I graduated with my bachelor's degree, I actually ended up going into industry. And so my first job I got out of having my bachelor's was actually for an oceanographic research company. And our biggest customers, our clients, were the Department of Defense and the Air Force. And so we would go out into the field, similar to locations like this is the Army Corps of Engineer research facility in the Outer Banks. And we would build instrumentation, deploy instrumentation, collect data in situ, and then rapidly analyze them to give them to our customers. And it was during those years that I realized, wow, I really like working with my hands. I really like being able to build something, put it out into the field, collect data, and then come back and analyze that data. And so that really left an impression on me during that time. But after a couple of years in DC, we decided to move, and I took a job at the National Solar Observatory, where I was working with the Global Oscillation Network group called GONG. And there I was working as a scientific programmer, building pipelines, analyzing data similar to the magnetograms that you're seeing here on the image. And it was during that time that I started realizing, you know, I like what I'm doing, but I now kind of start think I can go back to grad school and like really solve my own problems, and like really am interested in doing my own research. And so Anne was just a couple of doors away, still at the University of Arizona, and she said, you should come back and start working in my research group. Let's start doing telescopic observations again. And so I started doing my own observing runs, going to the IRTF and collecting thermal infrared spectra of the moon and Mercury. and realized, okay, I'm ready to go to grad school. I now know what I want to do. This is what I'm passionate about. I want to study airless bodies at thermal infrared wavelengths. And so off I went to Brown University, where Carly and Mike Wyatt and Jack Mustard were my advisors. And, if you're going to study the moon and you're going to do spectroscopy, that's a pretty fantastic group of advisors to have. So I felt pretty lucky. And I was also felt pretty lucky because I had the opportunity to work on 2 space missions. I was part of the Moon Mineralogy Mapper team. I was also a part, and still am a part of the Diviner team. And that really gave me an idea of how wonderful and unexplored the moon really was. And so during grad school, I started thinking about what really excited me about my work when I worked for Arete, and also at Gong, and also what I was learning at Brown. And I realized that what really motivates me or excites me isn't just sitting behind a computer, but instead is really doing it all. Meaning, I really wanted to take samples that we had collected on the moon, put them in environment chambers in the lab, measure those samples at thermal infrared wavelengths, and then compare them to what we were measuring with the Diviner instrument. And that's really what really fulfilled me and, made me feel like I was being a good, full lunar scientist. And so, we've been really lucky in the past few years because we've had a plethora of remote sensing observations, and Diviner is certainly one of them. And it's allowed us to use that data set along with other remote sensing observations, which has really enabled our probing of the lunar crust and how that crust formed and evolved over time. But what we've also learned is, while it is great to have all this remote sensing data, we do need lab measurements, and we need really good lab measurements measured under what we think are simulated lunar conditions, and also of very well characterized samples. And so, certainly the Apollo samples have been really fantastic, but boy, I would really love some new samples that we could put in these experiment chambers. And so one thing that in my career that I've really focused on is really understanding how to best simulate the lunar conditions in these environment chambers. And I've spent a lot of time with other Diviner team members, including Neil Bowles and Ben Greenhagen and Tim Glotch and his research group, to really best understand how to characterize that. And so in these bespoke environment chambers, we can essentially remove all the atmospheric gases to simulate an airless body environment. We can cool the chamber so that the body is radiating, or the samples are radiating out into a coolness of space. And then we can illuminate those samples with lamps similar to what the sun does to the lunar surface. And when we put our samples in there, we get really fantastic thermal infrared spectra, which we can then compare to these Diviner observations and really ground truth the Diviner observations, but also better interpret areas away from the Apollo landing sites. And so here are just a few spectra, because I feel like I should show some spectra, highlighting both the Diviner data for 3 different sampling stations at the Apollo 16 landing site. Those data are in black, and then all of our lab measurements in blue that have been resampled to the Diviner data. And, this is just 3 spectra or 3 plots, but that took a lot of effort and a lot of time to really hone and develop those techniques to really get lab data that really is close to the Diviner observations. And, that's certainly very exciting. And so you might say, okay, well, we have Diviner, we have all these trillions of radiometric observations from Diviner, and you now have figured out how to do things in the lab. What else is there to do? And these are just a few things that I'm really excited for coming into the future. One, there's so many lab measurements that are still to do, especially if we can get some new samples. there's a common theme here, more samples. And then, there's lots of new data to collect still with LRO. And we have new observations coming from Lunar Trailblazer and LCIRRUS and Lunar Vice, and then, hopefully LEXO. And I think what's really the most exciting aspect is we have had orbital data, for decades of the moon, and we've certainly used those to unravel new and interesting things. But I think it's going to be the surface observations that we get from rovers and landers through PRISM and CLIPS that are really going to unlock new challenges that are going to push us forward in our understanding of the moon. And so while that panics me a little bit of what's to come, it also really excites me. And so for the thank you portion, I want to go through and thank some really key people throughout my career. Obviously, I've had a lot of fantastic official and unofficial advisors, from Carly and Jack and Pete Schultz at Brown, to Dave Page and Carl Allen on the Diviner team, to Neil Bowles at the University of Oxford, and then Jess Sunshine and Ann Sprague. I've really tried to take what I've learned from each of you and take the best of that and use that with my own research group and also students in the community, and also with the Lunar Vice team. I'd like to thank my Diviner and MCube team members. Growing up within those teams, I feel like they really are my family. I still enjoy doing science with them, and being friends with them and hanging out with them and going out into the field with them. And I think the fact that we have such strong bonds really goes back to how those teams were led by Carly and Dave. And as Brett mentioned yesterday, the lunar science community and the SSERVI community is really fantastic. And I feel lucky and appreciate all of you that has allowed me to grow into the scientist that I am. I'm also super lucky, or I feel super lucky, about having some of those colleague members on my Lunar Vice team. And I'm excited to have you help me and get to the domes and get the best data that we possibly can for the science community. I'd like to thank my research group. So this includes undergraduate students, graduate students, and postdocs that were with me at the University of Oxford and now at the University of Central Florida. Coming in daily and seeing their excitement for research and seeing their successes in their careers really invigorates me and keeps me motivated even on some of the most hectic and challenging of days. And then finally, I'd like to thank my husband, Jason, who is always up for adventures, even if it's moving from one side of the country to the other, back to the other, and then back to the UK, all in the name of my passions and interests. And certainly in the past year has been my biggest cheerleader. And so I'd like to end with just a bit of early career advice, as Brett did yesterday. One, hopefully you take away from from my talk that you don't have to worry if your path looks different from others. Certainly you can still be successful if your path to lunar science or planetary science looks different from others. Find projects that you're passionate about. It's certainly hard. And if you don't enjoy what you're doing, it's just even harder. Try to find people that you really respect and enjoy to work with, because that certainly makes it a lot more fun and certainly keeps you more motivated. And always, think about, you don't want to be afraid to say yes to new directions, especially if they're things that might make you feel a bit uncomfortable. But as Brett said yesterday, you also need to know how to say no. And so with that, I thank you for listening.